In the previous video, we created a transformer from scratch for text classification and achieved a fairly accurate result. We used a simple single-hit attention mechanism and positional encoding to capture relationship between words in a sentence. Then we utilized a basic feed-forward network for classification. Now, in this video, we'll delve into building a transformer for language translation using multi-head attention. For this task, we'll be using an English to French translation dataset. Concepts such as masking and the construction of multi-head attention using self-attention were not covered in the previous video, but are covered here. So I strongly recommend watching the Attention is All You Need video, linked in the description or provided here, as it is crucial not only for this video but for the entire series as well. Now, let's understand the workflow we will follow to create and train transformer for language translation. Firstly, we'll obtain a sample of English sentences and their corresponding French sentences. We'll then clean, pre-process, and tokenize them. These tokenized sequences will be fed into encoder to obtain the encoded representation of the inputs, which will then be used as input to the decoder. Both the encoder and decoder will be equipped with multi-head attention. We'll attach a loss function and an optimizer to the model and initiate the training process. Once training is complete, we can use a transformer to input an English sentence and generate a corresponding French sentence. So without further ado, let's dive into the coding. The link to the dataset is provided in the description. It's available on Kaggle and contains sufficient English and French example for training, especially for this task. Now load the dataset and extract it into current working directory. Next, open a Jupyter notebook to start writing code. Import initial but essential tools such as NumPy, Pandas, Seaborn, and TensorFlow to create our recipe. Enable memory growth to ensure TensorFlow doesn't occupy all your memory during initialization. Begin by loading the data and performing pre-processing steps. Convert all examples to lowercase and store them individually in the list. For each example, add start of sentence and end of sentence tokens. Define the number of most frequent words to include in the vocabulary. Utilize a Keras tokenizer to convert sequence of text into sequence of tokens. The filter parameter here will remove any kind of special character from the text. Using the word index, you can determine how many words are included in the vocabulary. Repeat the same pre-processing step for the French sample as well. Tokenization occurs at the word level, meaning that the different sentence lengths will result in different tokenization outcome, as illustrated. However, neural network requires a fixed size input vector. So we'll use paired sequences to convert sequence into fixed size vector. What it do is add additional zeros at the end of the token to ensure the uniform sizes. In this case, the size of each vector will be 10. And with this, the dataset preparation is complete. Now let's proceed to build the model. To construct the model, we'll need positional encoding to retain the word sequence information, masking to enable masked attention in the decoder, and scaled dot product attention, which we'll use to create the multi-head attention. Additionally, we'll incorporate multi-head attention layer to form an encoder and decoder architecture. So let's proceed with building it. Create a function to generate angles for D dimension, a component of equation that aids in positional encoding. Now, develop a function to perform positional encoding for embedding dimensions length, generate angles using this function defined earlier, and create sine waves for even indices and cosine for odd indices as the equation says. You can test this function using arbitrary number to generate position sine and cosine waves. Create a padding mask, and the padding mask is applied to input to set the attention weight for padding tokens to 0. This ensures that they do not contribute to the attention computation. The look-ahead mask is used during the decoding phase of transformer. It's employed to prevent the decoder from attending to future position in the sequence when predicting the next token. This mask ensures that the model generates predictions based on the tokens that have been already generated, simulating an autoregressive behavior where the model generates tokens one by one. Now combine the padding mask and look ahead mask to create the final masking for decoding. This ensures that the decoder attends only relevant portion of the input sequence and previously generated tokens. The masking part is now complete. Let's move on to creating the attention mechanism. We'll use the same scale dot product attention as in the previous video. It takes query, key and value as parameter, performing matrix multiplication between query and key, and the result is divided by the square root of the dimension to scale the output. If the masking is enabled, it means the attention is being used in the decoder. Masking effectively excludes certain position in the input, such as padding tokens of future positions as explained earlier. With the attention mechanism ready, let's use it to build the multi-head attention layer. This layer will take the dimension of key vector, the desired number of attention heads, and the dropout rate for regularization. Make sure you choose dimension and the number of hit in such a way so that each attention head can look at even part of the vector. Create query, key, and value vectors, applying dropout with a specified rate. Reshape the tensor into a shape that allows splitting across the attention head. For the forward pass, get query, key, and value from the function parameter. Split the input vector into multiple head using split head function. Compute attention using the scale dot product attention. Combine the split attention vector. Pass them through the final dense layer and apply dropout to obtain the attention output. Create a feed-forward layer to obtain the encoded representation from the encoder. This representation will be fed to the decoder. The attention portion is now completed. All that remain is building the encoder and decoder. So let's proceed with building them. Create an encoder layer to construct the encoder. This layer will take embedding dimension, the number of attention head, the dimension for the fully connected network, and a dropout rate for regularization. Initialize the multi-head attention layer, normalization layer, and dropout layer. Finally, create an instance of feed-forward network to obtain the final encoder output. During the forward pass, obtain the input tensor, a flag indicating whether the model is in training mode, and the mask. Get the attention using multi-head attention, apply layer normalization to the input tensor, and pass the result to the feed-forward network. Normalize and return the output. Now use this layer to build the encoder. This function will receive number of encoder layer to be used, the dimension of embedding vectors, the number of attention head to be used, the number of fully connected network, the vocabulary size, the maximum sequence length for positional encoding, and the dropout rate for regularization. Initialize the embedding layer, positional encoding, and the specified number of encoder layer and the dropout layer. During the forward pass, get the input tensor, training flag, and mask from the parameters. Determine the input sequence length, pass the input through the embedding layer, scale the input sequence, and add positional encoding. Now apply dropout and pass the input sequence through each encoder layer. Return the final output. With this, the encoder section is also completed. Now let's move on to building the decoder. Create a decoder layer taking the embedding dimension, the number of attention head, the dimension of fully connected network, and the dropout rate from parameters. Initialize two multi-head attention layer. The reason for having two layers will become clear in the forward pass, so don't worry about that. Initialize the feed-forward network, several layers of normalization, and a dropout layer. During the forward pass, receive the input tensor, the output from the encoder, and the training flag. and the look ahead mask for the attention and the padding mask for attention. Use the input tensor as query, key, and value in the attention layer with the look ahead mask. Normalize the output from the attention using layer normalization. Then pass the output from the encoder as value and key and the output from the first attention layer as query along with the padding mask. The first attention layer receives one input tensor for the query, key, and value. The second attention layer takes two input from the encoder's output and one input from the output of first attention layer. This explains why two multi-head attention layers are used. Pass the output from attention layer through normalization, feed it to the feed-forward network, apply dropout, and normalize again to obtain the final output. Now we can use this decoder layer to build the decoder. Create a decoder layer specifying the number of decoder layers to be used, the dimension of embeddings, the number of attention heads, the dimension of fully connected network, the size of the vocabulary, the maximum length for the positional encoding calculation, and the dropout rate. Initialize the embedding layer to obtain embeddings from the input sequence, positional encoding, and the specified number of decoder layer and the dropout layer. During the forward pass, get the input tensor, the output from the encoder, the training flag, the look ahead mask, and the padding mask. Pass the input through the embedding layer, scale it, and add positional encoding, apply dropout, and feed it through each decoder layer. If you wish to visualize attention weight, record them at each step. With both encoder and decoder ready, it's time to combine them and create a transformer network. Construct a transformer model using Keras model. Specify the number of layers in the encoder and decoder, the dimension of input embedding, the number of attention head, the dimension of fully connected network, the size of input and target vocabularies, the maximum length for positional encoding, and the dropout rate. Initialize the encoder and decoder layer with the required parameters. Add a final softmax layer to obtain the final output. During the forward pass, provide the input sequence, target sequence, training flag, encoder padding mask, decoder look ahead mask, and the decoder padding mask. Pass the input sequence through the encoder to obtain the encoded representation, which will then be passed through the decoder with the target sequence, look ahead mask, and the padding mask to generate the final output vector. Feed this output vector into the final softmax function to obtain the final prediction. Now that the model is ready for training, let's define the variables and hyperparameters for it. Define the embedding dimension for both input and target sequence, the dimension of fully connected network, the number of layers in encoder and decoder, the number of attention heads, and then the dropout rate. These are the model hyperparameters. Define the size of input and output vocabularies, adding 2 to cover start of the sequence and end of the sequence. Specify the maximum length for positional encoding in both input and output sequences. Define the number of epochs and batch size for training. For stable model training, use the warm-up and exponential decay learning rate schedule instead of constant learning rate. This approach leads to faster and more effective conversions. The warm-up phase ensures a solid initialization, while the decay phase allows the learning rate to decrease as optimization stabilizes. This adaptive learning rate schedule minimizes the need of trial and error tuning. Create an instance of the model with the specified parameters. Define the optimizer and the loss object for computing training loss. Define the loss function, which will take true result and the predicted result as parameters. Create a mask for padding tokens to exclude them from the loss calculation. Calculate the loss using the loss object and apply the mask to disregard padding tokens. Return the mean loss. Define the function to calculate accuracy. This function takes true values and predicted values. Compute the accuracy using the true and the predicted values. Create a mask from the true values just as in the loss function to exclude padding tokens. As padding tokens are zeros and do not contribute meaningfully to the sequence, they are excluded from the loss and accuracy calculation. After applying the mask, return the mean accuracy. Define training metrics to track loss and accuracy during training. Now define a function to train the model for single step. This function takes input from the encoder and target output, slice the input tokens from the decoder and expected decoder output. Create padding mask for both the encoder and the decoder as well as the combined mask for padding and look ahead for the decoder. Using gradient tape, feed the input into the model to get the prediction. Calculate the loss using loss function and compute the gradient using this loss. Update the model parameters using the gradient descent optimizer. Update the training loss and accuracy. With the training step function prepared, let's proceed to train the model. For each epoch, reset the previous training loss and accuracy states. For each batch, prepare the batch as input tensor and pass it to train step function to train the model on that specific batch. Print the loss and accuracy at the end of each epoch to monitor the model's performance during training. Note that the training process is underway. You can observe how the GPU is utilized. And as you can see, the loss is decreasing over epochs. The training part is skipped here due to its time-consuming nature, as it takes several hours to reach 100 epochs. Once training is completed, a considerable accuracy improvement can be observed after 100 epochs. You can save the model weights for future inference. Now let's move on to writing code for model inference, which involves taking an actual English input sentence and generate the corresponding French output. Define your input text and add start of the sentence and end of sentence tokens to it. Tokenize and pad the input sequence as well as the output sequence. Create masks for both the encoder and decoder using the input and output sequence. Create a list to store the output sequence at each step. And for each step, feed the input and output sequence along with the mask into the model. Obtain the predicted token with the highest probability at each step. Exit the loop when the model predicts in of the token. Store the predicted tokens in the output token list and update the output sequence with the most recently predicted token. Update the mask for the output sequence. Once the loop concludes, convert the output token to a tensor. Use this output sequence tensor along with the French tokenizer to obtain the text. Similarly, you can convert the input tokens to text using the English tokenizer. If desired, you can verify the output using Google Translate to assess its accuracy compared to the model's prediction. And that concludes our endeavor. We have just created a transformer model from scratch using TensorFlow for language translation. And here are 3 things you can remember from this video. Multi-head attention mechanism allow the model to capture rich contextual information by attending to different parts of the input sequence simultaneously. Properly applying padding and look-ahead masks ensure that the model handles variable length sequences effectively during training and inference. Including positional encoding is crucial to provide the model with information about the order of tokens in the sequence, compensating for the lack of inherent sequence understanding in transformer architecture. Given the comprehensive nature of this video with extensive code, some minor explanations might have been missed or skipped. Feel free to ask them or any type of question in the comments. In our next video of this series, we'll construct a text summarization model from scratch and we'll employing a new attention mechanism. Until then, enjoy the learning and continue to build models that solve problems. I'm truly grateful to all of you, and as always, thanks for watching.